Maximum work obtainable from two identical systems. Consider two identical bodies A1 and A2, each characterized by a heat capacity C which is temperature independent. Identical bodies, heat capacity C. The bodies are initially at temperatures T1 and T2, T1 greater than T2. Initially, it is desired to operate an engine between A1 and A2 so as to convert some of their internal energy into work. As a result of the operation of the engine, the bodies ultimately will attain a common final temperature T final. What is the total amount of work done by the engine? Okay. So here is the schematic diagram. A1 is at higher temperature, T1, so therefore it's red, it's hot one. A2 is at temperature T2, which is cold. We're absorbing heat from the A1 reservoir, extracting or releasing heat to the A2 reservoir and getting some useful work output. And we have T1 greater than T2. If you look at the internal energy change of the engine, because it's a cycle, it is 0. The total amount of heat absorbed is Q1 minus Q2. And the work done on the engine is minus W. So this is going to be equal to 0. Therefore, I find that the work done by the engine is Q1 minus Q2. So minus W is work done on the engine. This is W on the engine. And this is the heat absorbed. Q1 minus Q2 is the heat absorbed. So it's Q plus W on. This is the first law. First law of thermodynamics. So therefore I need to calculate Q1 minus Q2. So what is the infinitesimal amount of heat released by A1? It is its heat capacity minus heat capacity dt, because this is released by A1, and the infinitesimal amount of heat absorbed by A2 is plus CdT, that is absorbed by A2. Okay, so I just have to calculate these integrals. So the work done by the engine, W, is going to be equal to the integral from T1 to T final d bar Q1, that is Q1, and minus the integral from T2 to T final CdT, this is d bar Q2, so this is basically going to give me Q1 minus Q2. Okay, so what is this equal to? W is the integral from T1 to T final. D bar Q1 is minus CdT over T, and minus the integral from T2 to T final plus CdT over T. So this will give me minus C T final minus T1 minus C T final minus T2. So as you can see, I'm going to get in C parentheses T1 plus T2 minus 2T final. So my final answer, work done by the engine, is C times T1 plus T2 minus 2T final. Let's move on to part B. Use arguments based upon entropy considerations to derive an inequality between Tf and the initial temperatures. So what is the total entropy change? Entropy change of A1 is basically the heat it is providing. So it is the integral from T1 to T final, the heat it provides minus d bar q1 divided by T, because minus d bar q1 would be the one that is absorbed. So this would be equal to then integral from T1 to T final plus CdT over T, which is C natural logarithm T final over T1. And similarly, for the entropy change of the A2 system, I have integral from T2 to T final. It's the heat absorbed d bar Q2 over T, which is integral from T2 to T final, CdT over T, which is C natural logarithm T final over T2. So if I write the entropy change of the pump, this is a cyclic process, so it is 0. Therefore, the total entropy change, delta S star, is delta S1 plus delta S2, which is equal to C natural logarithm T final over T1 plus natural logarithm T final over T2, and this becomes C natural logarithm T final square divided by T1 T2, and this must be greater or equal to 0, second law of thermodynamics. So I find that natural logarithm of T final square divided by T1 T2 must be greater or equal to 0. So if I take e to the natural logarithm, e to 0, this is going to become T final squared divided by T1 over T2 must be greater or equal to 1, which means T final must be greater or equal to square root T1 T2, the geometric mean of the two temperatures. Part C. For the given initial temperatures T1 and T2, what is the maximum amount of work obtainable from the engine? So I look at the work, it is C times T1 plus T2 minus 2T final. So I want to maximize this. How do I maximize it? T final must be a minimum because I'm subtracting 2T final. So therefore, T final must be equal to its minimum value, square root T1, T2. So W maximum will be C times T1 plus T2 minus 2 square root T1, T2. Well, you can see that this is actually C times square root T1 square plus square root T2 square minus 2 square root T1 T2, which means the maximum value of the work is C times square root T1 minus square root T2 square. Okay, so we had two identical bodies, A1 and A2. First, we looked at the first law of thermodynamics, heat provided by A1, heat absorbed by A2. The difference is the total heat absorbed by the engine, Q. And minus W is the work done on the engine, so this must be equal to 0. The first law tells me W is Q1 minus Q2. The heat released by A1 is infinitesimal amount is minus CdT. Heat absorbed by A2 is plus CdT, infinitesimal amount. So the total work done will be the integral from T1 to T final d bar q1, which is q1, heat released by A1, minus the integral T2 to T final d bar q2, heat absorbed by A2. So that gives me C T1 plus T2 minus 2T final. The entropy change of A1 is the heat absorbed by A1, infinitesimal amount of heat absorbed by A1 is minus d bar q1 divided by T integrated from T1 to T final, that is CdT over T from T1 to T final integral. Delta S2 is d bar q2 over T, that is plus CdT over T, and if I add them up, I find that the second law tells me since the total entropy change must be equal to greater or equal to 0, T final is greater or equal to square root T1 T2, which means it has a minimum value square root T1 T2. In order to maximize the work done by the engine, I have to minimize the amount I'm subtracting from T1 plus T2, and that is square root T1 T2, so that gives me a maximum amount of work, C parentheses squared of square root T1 minus square root T